Sorry about that, guys. Having coughing fits is part of it, I guess. I don't know. Okay, so we were talking about the parts and pieces of this. You have the scala vestibuli and the scala tympani, which are the bony labyrinth. You've got the membranous labyrinth kind of between them. Both the scala vestibuli and the scala tympani have that liquid perilymph inside of them. The membranous labyrinth actually has the endolymph. Okay, so the end of this over here is called the helicotrema. Okay, so the reason that I'm pointing things out is because it actually does affect where sound is processed in this cinnamon roll, depending on pitch. So this membrane right here, okay, that I'm currently putting a red line on, is the vestibular membrane. It's actually a very thin membrane between the top of the membranous labyrinth and the bottom of the scala vestibuli. This membrane here is called the basilar membrane, and this is actually kind of where all of the interesting things happen, which we're going to talk about in just a bit. So when this stapes vibrates on top of the scala vestibuli, it creates waves in the perilymph. And depending on the pitch, whether it's high pitched like Minnie Mouse or low pitched like Barry White, it kind of determines where it crosses over to come back this direction. Okay, so there is directionality to these waves. They go around this way. Okay, so why? Why is there directionality? Well, you don't want sound waves bouncing back and forth like an echo. So if you look at how this is designed, at the end here is that round window. You can think of the round window kind of like a mute. Instead of allowing the sound waves to bounce around, literally it hits that round window and you're done. You have the ability to hear it and decipher what those sound waves mean once instead of having them repeat over and over and over in your brain. So you've got the scala vestibuli, the scala tympani, the vestibular membrane, the basilar membrane, the cochlear duct. Just so you know what abbreviations I'm using. Perilymph is in, as I said, the scala vestibuli up here and the scala tympani down here. Endolymph only exists inside of this purple balloon, the cochlear duct. Okay? So the cochlear duct, because in its natural form it's actually wrapped around like a cinnamon roll, is often called the spiral organ. And the scala vestibuli extends. So remember, the scala vestibuli is the top one. It extends from the oval window toward that helicotrema out here. Again, there's directionality to it, okay? The scala tympani, however, starts here at the helicotrema and ends at the round window. Again, direction, there's direction. The vestibular membrane, I'm going to erase this again. The vestibular membrane up here, okay? That is a thin membrane, like I said, between the scala vestibuli, this up here, and the cochlear duct. And it's so thin that there are no effects on sound wave transmission. Literally, the waves created in that fluid are just carried through because that membrane is so teeny tiny and thin. The basilar membrane is a lot more complex, and as far as our ability to hear, it's more physiologically interesting because the mechanics of hearing are all happening in this basilar membrane right here. Okay? As well, the width of the basilar membrane increases with the distance. So the closer to the helicotrema you get, the wider it becomes. So all I did was I took this cinnamon roll and I cut it like this. So now you're looking at it directly from the cut cinnamon roll viewpoint here. Okay. The basilar membrane has two major regions. You have an acellular portion. In other words, it's not made of cells. Acellular, no cells. It's made of collagen fibers, of ground substance, and of sparse elastic fibers. So fibers are not living cells. They're just kind of, well, they're fibers. Elastic fibers have the ability to stretch and bounce back. Collagen fibers tend to be very strong. Think of a belt. You can manipulate a belt and you can bend it around really easily, but if you try to yank that belt apart, it's got a lot of tensile strength. That's collagen fibers. Round substance is kind of like the filling. It fills the space. The cellular portion, though, you've got kind of this thin layer of vascular connective tissue at the bottom, overlaid with simple squamous epithelium. The collagen fibers near the oval window, so near the foot of the stapes, are short and they're very stiff. They only activate with high frequency vibrations. So Minnie Mouse's high pitched voice, you'd be closer to where that foot of the stapes is, where you're activating the basilar membrane. The collagen fibers near the helicotrema, near the end of that path, are more wide and they're more limber, meaning that high-pitched frequencies wouldn't activate them. In that case, it's going to be low-pitched frequencies. So if we go back to this here, if you're closer to this foot of the stapes here, it's going to be a high-pitched noise. If you're closer over here to the helicotrema, it's going to be a low-pitched noise. Barry White's voice, Morgan Friedman's voice. So looking at the spiral organ, the organ of Corti, guess who discovered it? Corti. So you've got, again, those supporting epithelial cells. Remember, these are the nanny cells. They watch, they take care of. These pink cells that you see, okay, are going to be the supporting cells. Then you've got hair cells. And the reason they call them hair cells is because they've got this little cowlick thing at the top. You've got kind of a single row of these hair cells on the inner side. And then you've got this triplet row out here of hair cells, okay? That inner row, that single inner row here, is going to be what's responsible for your hearing. Whereas the outer three, these guys here, okay, they're responsible for the tension that's kept in the basilar membrane. So one of the things with these cells is that they are mechanical cells. In order to get them to respond, you have to bend them. So by bending the hairs, you're sending signal. Well, if I've got to bend the hairs by crashing these cells up into this thing here, which is called the tectorial membrane, if I let them bang too hard, I'm going to kill the cells. So having a way to control how much movement there is in that basilar membrane is going to be important so that you don't damage these cells. And that's what this outer row of 3 cells does. If things get too wild and woolly, they tighten everything up and don't let the movement go so wild and crazy. So looking at that single inner row of cells, just this one right here. This one right here. I don't know what just happened, but that one right there. Okay. This is not the right slide. I switched slides, sorry. This one. Okay, that single inner row is responsible for hearing, like I said. And the hairs on it are going to form a cone structure. A conical bundle is what we call it. And you can see it right here. As that cone forms, they're increasing in length. You can see here that this hair is kind of small. The next one is a little taller. The next one is a little taller. The next one is a little taller. So you're getting this increase in length, okay? The top link, whoever is taller, actually connects with the neighboring cell. So you can see that here. You can see that here, where this tall hair is connected to this shorter hair. Now here's the dealio. When you bend these hairs toward the tall hair, these channels that are actually bound together from hair to hair open, and it's a physical movement of bending the hair that causes these channels to open. Now, once the channels open, ions can move into the cell. Ions move into the cell, you get an action potential. So that top link connecting to the neighboring hair cells is how we open these mechanically gated potassium channels, okay? You bend the hairs, the channels open, potassium rushes into the cell, you get an action potential. This isn't like we've seen before our weird palm tree. It isn't the classic axon, but it still is a neuronal cell. It's just that it is attached to, at its base, a secondary cell, kind of like what we saw when we were looking at the taste cells and what we saw when we were looking at the olfactory neurons. You can see here that they're communicating with a secondary cell. Okay, so the outer row. The outer row doesn't have that same kind of cowlick conical structure. Instead, the little hairs make arches, which you can see here. This is an electron micrograph, okay? So they are, as I said previously, responsible for the tension in the basilar membrane. They are separated from the outer cell by a gap. You can see here that there is a space between the single row of cells and the little triple row of cells. The hairs on the cells are arranged in a curved pattern like you see. And again, the longest one is embedded into this tectorial membrane. Okay, that gelatinous shelf that's sitting on top, that tectorial membrane. And they work in the same way. They have that connecting from the taller to the shorter hairs so that when they bend, it causes a channel to open and it causes signal to move. So let's talk terminology, auditory function terminology. Vibration. These are ripples propagated along matter. The best example that I can think to kind of share with you is if you have ever seen the original Jurassic Park and the kids are in the Jeep and the Tyrannosaurus Rex is coming and they show that cup of coffee with the rings going into it, right? Okay, how did they do that? They actually put a guitar playing the note G into the CD player. And every time, and of course, turn the volume up like crazy. Every time they strum that G note, it caused those concentric circles. That's vibration. That's going to be ripples propagated along matter. Volume is a function of wave amplitude or height, and it's measured in decibels. So if I were measuring, let's say, sound waves, and this is one volume at low volume, I want you to notice where the bases of these are. If I turn up the volume, the size of the wave changes as far as height, but the distance between the waves doesn't. So when you turn up the volume, you're not changing the sound, you're just changing how loud it is. Pitch, however, actually does change the wave pattern. When you're talking about pitch, you're talking about how frequent the waves are. The more frequent the wave, the higher the sound. Okay? So higher pitch sounds will have more waves closer together. Lower pitch sounds will have waves that are further apart. Okay, so pitch is a function of wave frequency, the number of waves per second, and it's measured in hertz. High frequency, in other words, you have a lot of waves in a very short space, that's going to be high pitched. Low frequency, few waves in that same space, you're going to have a lower pitch. Now, timbre. I know it reads timbre, but it's actually pronounced timbre, and I just recently learned that. The resonance quality or overtones of a sound. When I read that, I went, what now? Okay, think about it this way. I can sing a middle C, right? I can use my voice and I can sing a middle C. I can go to piano and I can play a middle C. I can take a trumpet and I can play a middle C. I can go to a guitar and play a middle C. But you would never mistake my voice singing that note as a guitar string being plucked. You would never mistake my voice singing that note as a trumpet playing the same note. There is a certain resonance quality or an overtone to the sound. So the timbre is that difference in sound. Even though all four things are playing the same note, there is definitely a difference to the quality of the sound. So for us, normal hearing range is between 20 and 20,000 hertz and 0 to more decibels. But when it comes to decibels, we start getting to 125 or higher, and it starts to become painful. If you've ever been around something that is so loud that it kind of makes you cringe, that's when you're getting into pain territory instead of just audio territory. So, sound wave comes in. It passes through the auricle and the external auditory meatus, and it hits the eardrum or the tympanic membrane. That causes the malleus to vibrate, which in turn hits the incus, which in turn, because I'm connected to it, makes the stapes move. As the stapes moves back and forth, because it's vibrating, it causes waves in the perilymph. Okay? So the vibration of the perilymph causes that vestibular membrane to also vibrate. That in turn carries into where that endolymph is. The vibration of the endolymph actually displaces the basilar membrane, meaning that it's hitting that tectorial plate, okay? So you've got short waves causing displacement closer to where the foot of the stapes is, okay, near the oval window. And you've got longer waves going further, causing displacement closer to the helica trema. The vibrations of the perilymph in the scala vestibuli and of the basement membrane are transferred to the perilymph from of the scala tympani. So they're going, like I told you before, in one direction. Why? Because once they get to the scala tympani down here, they get to that round window where they're dampened, where the sound stops, where the waves stop. Why? Again, because I don't want to hear echoes. I don't want to hear echoes. I just want to hear it once, and that's the end of it. So, going through the external ear, the auricle directs the sound waves to the external auditory meatus and to the tympanic membrane. It's a funnel, it's funneling it down to the tympanic membrane. Sound waves are actually fairly slow. They only move about 332 meters per second, and that means that sound waves actually hit your ears at different time points because you've got your ears on completely opposite sides of your head. If you close your eyes and have somebody walk around a room, you don't have to open your eyes to point to where they're standing, because wherever they're standing, your ears are going to tell you it reached this ear faster than it reached that ear. And I know that sounds weird, but it does work. In the middle ear, you've got that tympanic membrane vibrating from the external ear through the ossicles. The malleus vibrates with the tympanic membrane, and in turn, it hits the incus. The incus, in turn, vibrates the stapes on the oval window. You do kind of run into an issue here, okay? Going from the middle ear that is full of air into the inner ear that is full of fluid. That switch from air to fluid, from air to perilymph, actually is pretty difficult to deal with because you're basically going to have to increase and amplify that vibration quite a bit. So how do we do that? Well, the tympanic membrane is 20 times as big as the stapes foot at the oval window. So that alone actually amplifies those sound waves quite a bit just because of the mechanical differences in how much they move and the physical difference in how big they are compared to how small they are. In the inner ear, the vibration of the foot plate of the stapes, so where you'd put your foot in that stirrup, causes the perilymph of the scala vestibuli, that top tube, to vibrate, which in turn vibrates the vestibular membrane, which transmits that vibration to the endolymph. The endolymph causes the BAM, the basilar membrane, to move, to vibrate. That's where the hair is. The hair is sitting on top of it. Short waves or higher pitch displace hairs near the oval window where the foot of the stapes is. Longer waves or lower pitch displace the hairs closer to the end where that helica trema is. Hair cells are bent because that tectorial membrane, that gelatinous mass that's sitting on top that I pointed out, doesn't move. So if the base is moving, it's coming up to meet that tectorial membrane. So in an unstimulated ear, about 15% of the channels are open at resting membrane potential. When nothing is happening, the resting membrane potential of the cells is about negative 60 millivolts. If the hairs are bent toward the short hairs instead of toward the long hairs, it'll actually cause the inside of the cell to become hyperpolar. It'll become even more negative than resting membrane potential. Now, hairs bent toward the long hairs, the stereocilia, will basically be a positive stimulus. It causes the channels to open, the ions can flow in, and you're going to induce an action potential. So literally, I'm preventing it from happening if I go toward the short hairs, but I'm causing it to happen if I go toward the long hairs. So the neuronal pathway. The sensory axons from the cochlear ganglia actually terminate in the cochlear nucleus of the brainstem here at number 1. Okay? So the axons from the neurons in the cochlear nucleus actually will project up to the superior ovulary nucleus, or okay, superior ovulary nucleus, or, sorry, to the inferior colliculus, which is a little bit further down here. Axons from the inferior colliculus project up to the medial geniculate nucleus, which is the one that's actually up here. And those project to the medial geniculate nucleus of the thalamus. The lambic neurons project up to the auditory cortex up here, okay? Neurons in the superior ovulary nucleus will also send axons to the inferior colliculus and back down to the inner ear. There's actually another path coming down here, okay? Now, why? Remember we talked about being at a concert and the sound waves being really, really big and hurting your ears, so those muscles have to relax? Those muscles have to relax and contract, and that's in response to what you're hearing. So there has to be a feedback down into your ear to control those types of things.